Hello there, everyone. Good afternoon, and welcome to another Royal Astronomical Society's online public talk. Hello, I am Lucinda Offer, Education and Outreach and Events Officer for the Royal Astronomical Society. And we also have Dr. Louise Alexander with us from RAS Editorial doing Q&A today. So our organization advocates for astronomy, geophysics, and space science in the UK since 1820. And if you're interested in astronomy and geophysics and enjoy our lectures, then you might be interested in the Friends of the RAS membership program. Friends of the RAS have access to 6 to 8 additional talks like this every year, as well as discounted rates on our astronomy and geophysics magazine and use of our incredible historic library, which is reopening by appointment this Friday. Membership is £40 for the year. Please visit our website, ras.ac.uk, for more information. Today, I'm really excited to introduce to you our public lecture guest speaker, Giulia Magnarini, who will speak with us about megalandslides on the Earth, Moon, and Mars. Giulia has recently finished her PhD in the Department of Earth Sciences at UCL, where she studied the formation mechanism of long-runout landslides. She's now a postdoctoral research assistant at the Natural History Museum in London, working on recent and active surface processes on the Moon. Her current research mostly focuses on lunar fault activity, lunar landslides, and impact cratering. She also continues studying long-runout landslides on Mars, focusing on their relationship with Martian tectonics and climate history. Giulia is involved with the NASA Apollo Next Generation Sample Analysis Program, otherwise known as ANGSA, studying a recently opened Apollo 17 sample that was collected from a landslide deposit. And I do believe she's going to share that with us today. So some very exciting stuff ahead. A quick reminder that there will be a Q&A after the talk hosted by the lovely Dr. Louise Alexander. So please get your questions ready. There are places to post your questions for our speaker if you've joined us on Zoom in the Q&A box and on YouTube in the chat box. Thank you so much, Giulia, for being with us today. On to you.
Hello, everyone. Thank you, Lucinda, and thanks, Louise. Thank you so much for having me here today. I'm really happy to be able to talk about long-runout landslide. I'm really happy to be able to talk about this incredible landslide on Mars, Earth, and the Moon that I studied for my PhD, which, as Lucinda mentioned, I just recently finished. And before diving into the presentation, I just want to make sure that we are all on the same page and that everyone is aware what a landslide is. Although I'm pretty sure that all of us have heard about landslide at least once in the news, because they tend to disrupt roads, railways, usually after a period of heavy rains. Anyway, so with landslide, we mean a mass of rock that move down a slope. So for instance, it's a slope that could be like the slope of this mountain we have here on the slide. So it's a mass of rock that move down a slope under the effect of gravity and then form a landslide deposit at the base of the slope. In the title here, I use the term mega, but in reality, the landslide I'm going to talk about today are called long-runout landslide. And as the name suggests, these are landslides that move much farther away from their source area than we would normally expect. But I hope that by the end of this presentation, you will agree with me that this landslide have a truly remarkable behavior, and so that the use of mega is somehow justified in the title. I didn't tell you that the landslide we have here on this slide is the landslide that the Apollo 17 astronaut, Jim Cernan and Harrison Schmitt, who was the only geologist to go to the moon, yes, is this landslide here that we will talk about later in the presentation. And this is the only extraterrestrial landslide that have been explored by humans so far. Another thing that I don't mention in this slide, or at least I don't give you, is the scale. And so it becomes difficult, if actually impossible, to have an idea about the height of the mountains, for instance, or the length of the landslide. But this is something that I would like you to try to do. But because we are going to talk about this landslide later, I will ask you to try to guess the size, the dimension of this other landslide. This is on Mars. So this is an oblique view of a 3D reconstruction of a landslide. Unfortunately, unfortunately, not the entire landslide. I was able not to reconstruct the entire landslide with this 3D model. But I would like you to try to guess how long this landslide is. And you can see it originated from a mountain range. We can clearly see where the where a section of the slope broke and moved downwards under the effect of gravity, and generating this really beautiful fan-shaped deposit with these incredible continuous linear features that we call longitudinal ridges. So I want to also to pay attention that these deposits run over a subhorizontal surface. So I'm asking you, how long do you think a landslide could actually move over a subhorizontal surface? Do you think will be few meters, kilometers? So I give you a few extra seconds maybe to place your bet on the size of this landslide. All right, so I'm going to reveal the answer now. So this roughly circle-shaped shape in purple color is the M25 motorway around London. And so we can see that this landslide has dimension comparable to the M25 motorway around London, which is quite big if we consider that from east-west, it extends for about 55 kilometers. And I also place some London landmarks in between, so to give a better idea of the size. And north-south is about 45 kilometers. It's quite a big of a landslide. And if we squeeze the entire deposit, even the part that is not included in this model, if we squeeze the entire deposit within the M25, we will cover it under 200 meters of rock. So it's pretty big landslide, and think that we can actually have even bigger landslide, but we can also have more modest landslide. And so we may ask, okay, how then we define what is a long-runout landslide? What are their characteristics? To do so, I'm using an extract from the second book of the Mars trilogy, Green Mars, written by Kim Stanley Robinson. And in this book, a couple of pages are dedicated to long-runout landslides. And the scene is set in Valles Marineris, which is the big canyon on Mars that we have here in the background of the slide. And Anne is one of the protagonists. She's a geologist and she's exploring the area. I'll try to read the passage. A motion caught her eye, landslide. The cliff face disappeared in the rising cloud of dust. A distinct boom, followed by a faint roaring like distant thunder. The collapsed headland had to be millions of cubic meters of rock. She realized with a start that she was witnessing a long-run-out landslide. They were a strange phenomenon, one of those unsolved puzzles of geology. The great majority of landslides move horizontally, less than twice the distance they fall. But a few very large slides appear to defy the laws of friction, running horizontally 10 times their vertical drop, and sometimes even 20 or 30. These were called long-run-out landslides, and no one knew why they happened. All right, so I highlighted in bold two passages of this page. And one is telling us that the horizontal extent of long-run-out landslide is several times, many times the vertical drop. And so it's this exceptional horizontal runout compared to the vertical drop that define a long runout landslide. And the other part of the text in bold is a reference to the volume. And we know that this exceptional runout is observed for landslides that are larger than 1 million cubic meters. And if we want to get an idea of what a million cubic meter is, we may want to think about, for instance, 400 Olympic swimming pools. Or if you prefer, we can think about 11.5 Royal Albert Halls. So it's kind of gives the idea about the big size of these landslides. So on Earth, the first long runout landslide to be described was the landslide in Austria in 1881 by the Swiss geologist Albert Heim. So Albert Heim went to the site of the landslide soon after the event, and so to study how the landslide behaves. So study the deposit, having a look at the source area, and also gather information from the witnesses. And he realized that this landslide, the Elm landslide, was characterized by an exceptional mobility. So he realized that it moved for several tens of meters per second. That for a landslide is quite fast. It's quite a fast landslide. And then he noticed that the landslide was able to move so fast for a bit more than 2 kilometers and over a subhorizontal surfaces. And in addition, he realized that water was not a dominant element in the landslide. And this was somehow odd, because we usually think that usually water help the transport of dry rock debris, and sometimes to the point that actually the rock will behave like a fluid. And so since the early work of Albert Heim, many other long runout landslides have been identified and studied. And we now know that the larger is the landslide, the longer the higher its mobility. And yes, so many, as I said, many other landslides have been identified, and we have here some example. Here to the top left, we have a 19 kilometers long landslide in Iran. And again, note the subhorizontal surface over which they extend for so many kilometers. And another thing I would like to pay attention, here I colored in yellowish a hill. So like an obstacle that the landslide encounter during the runout. But look how the landslide just ran over it, undisturbed, like nothing was in the middle. And these other landslide to the top right is another example of long runout landslide. This is in Kyrgyzstan, slightly bit modest size. It's only 3 kilometers long. But again, look at the subhorizontal surfaces over which they are able to move for so many kilometers. This is another terrestrial example, the El Magnifico landslide in North Chile. And this is actually one of the landslides I did study for my PhD. It's 4 kilometers long, and you can clearly see the source area from this cliff that is 700, 800 meters high. And look how, this landslide was able to extend for 4 kilometers, moving over a subhorizontal surface, low inclination surface. And so many mechanisms have been proposed to explain this behavior of long-runout landslides. So what could explain the fact that it moves so fast for so long, so many kilometers, and over sub-horizontal surfaces. One of the first ideas that were proposed was the presence of a air cushion layer at the base of the Black Hawk landslide in Southern California. This is about 8 kilometers long landslide. And so this idea envisioned the presence of a sort of air pocket below the landslide, in between the landslide and the surface over which it moved, and so creating a extremely low friction surface over which this landslide would be able to extend for, in this case, 8 kilometers. Other hypotheses instead involve the importance of frictional heating. And frictional heating is the heat that is created when two objects slide one against each other. So for instance, if we take our hands and we place them together and then we start moving them one against each other, the more we press and the faster we move, we can notice that it becomes warmer, okay? And this is frictional heating. That's what we are talking about. And so in the case of big landslide, frictional heating is thought to be able to produce a layer of molten rock, and this layer at the base of the slide will facilitate then the runout. But also frictional heating is thought to be able to produce gases at the base of the slide. So for instance, releasing CO2 from carbonate rock. And so the release of this gas at the base of the slide would increase the pressure at the base, and this increase in pressure would be able to support some of the weight of this big landslide, and again facilitating then the runout. And then there is another, let's say, group categories of hypotheses that instead think that vibration caused by this catastrophic energetic event would be able to facilitate the runout. If we think about some industrial processes, actually vibration are used to move like granular flow, for instance, or some other type of object. So to facilitate the movement of something along not inclined plane or slightly inclined plane. But then we also have long runout landslide and placed on glaciers. And in these cases, ice, or at least the slippery surface provided by ice, is considered the dominant element in facilitating, enhancing the runout of the landslide. In this case, it's a very iconic example of a long runout landslide on a glacier, the Sherman Glacier landslide in Alaska. And this was triggered by the Great Alaska earthquake in 1964. And he originated from this mountain here that I highlight with this red line. I don't give you the distance, but the landslide extend for 4 kilometers. And again, here in yellow is a spur, and look how the landslide just simply ran up over it like nothing happened, and just continue for the last 2 kilometers on the glacier. Yes, so this is another long runout landslide on a glacier, slightly longer. This is 5 kilometers. This is a fairly recent one. This happened in 2016. And another thing I would like you to pay attention to long runout landslide on glacier that actually I didn't mention earlier are this longitudinal, this linear feature that mark the deposit of this landslide. Then we can, I hope you would be able to see this linear feature that we call longitudinal ridges, and that mainly appear towards the lateral and frontal edges of the landslide. And actually, the similarity of terrestrial landslide and placed on Glacier and some Martian terrestrial landslide has been used to suggest the presence of ice on Mars at the time the landslide happened. So this is again a 3D representation, reconstruction of a Martian landslide. This is 28 kilometers long. So these are kind of like an order of magnitude bigger than terrestrial landslide placed on glaciers. But I'm pretty sure we can see some similarity with terrestrial landslide on ice for the shape that we can call morphology of the landslide deposit, and also on this linear feature, again, that they appear here. These are other landslides on Mars. These are like a group of landslides. We can recognize many. Here to the left-hand side, we have probably at least 3 or 4 landslides, one on top of each other. To the right-hand side, instead, we have 2 opposite landslides overlapping. And these are one of the first landslides that were photographed by the Mariner 9, the NASA Mariner 9 mission to Mars in 1972, and then following with the Viking mission in the mid-70s. And these are the landslides that were first, let's say, compared to terrestrial landslide on Glacier, for which some type of similarity was acknowledged, and especially, as I said, in this linear feature that mark the surface of the deposit. And these 2 images here are just a close-up view of the landslide we saw in the previous slide. And I honestly find it astonishing, the details of these features, and also the level of preservation of these landforms of Mars, if we consider that this landslide may be hundreds of millions of years old, if not more. So ice could be an hypothesis to explain the long-runout landslide on Mars. But apart from the morphological similarity with terrestrial landslide on ice, we don't really have compelling evidence for the presence of ice in these areas where these long-runout landslides are. And so some other hypotheses have then tried to find other alternative mechanism that would instead, let's say, would be an alternative to ice if ice was not present. And some other then hypotheses suggest that clay minerals, which have a platy structures that then in the presence of water will make the rock slippery. So the presence of this clay mineral may have facilitated the long run out of the Martian landslide. And some other hypotheses instead have suggested the presence of standing bodies of water like lake. And so some of the Martian landslide may have been subaqueous. And all these scenarios may not be actually difficult to imagine on Mars. But again, we don't really have strong, compelling evidence to say that landslide was subaqueous or that landslide was placed on ice. But these hypotheses, these remain plausible. And so all the hypotheses and mechanisms that I've listed so far have been proposed to explain the long run out of terrestrial and Martian landslide. But the majority of this mechanism will not be applicable to lunar landslide. So here we move to the moon. And why they wouldn't be applicable to the moon. So the moon is essentially considered a dry place and is an airless body. There's no atmosphere, and ice was never present in such quantity to form extensive glaciers. And the landslide we see here is called the Tsiolkovsky crater landslide that I try to highlight with this blue line, and then I hope it becomes a bit more evident in this white box here to the right, bottom right of the slide. And I hope you can somehow recognize as well on the moon some of these linear features we have seen so far. In both terrestrial and Martian landslide. This is the probably the first long run-up landslide to be identified on the moon during the Lunar Orbiter program. Lunar Orbiter 3 was the mission that firstly photographed this landslide in the early 60s. The other long run-up landslide on the moon that we know about is a landslide that I hope you remember from the first slide of this presentation. And finally, I provide you a scale bar so that we finally know that this landslide deposit is 5 kilometers long. The landslide is called light mantle, and it's kind of obvious why it's called light mantle, and the name comes from the color of the deposit that appear much brighter than the darker material that form the landslide deposit. This landslide came down this mountain here, which is called the South Massif. And as I said before, this is the only extraterrestrial landslide that was explored by humans and by the Apollo 17 astronaut in 1972. And I hope you can see this small bright spot over there, and that's where the lunar module Challenger landed in 1972. So the idea behind the formation of this landslide is that following an impact, the impact that generated the Tycho crater, which is this big crater that we can see here to the big image of the moon to the top right. So this big crater here, Tycho, following this impact, ejecta material travel across the lunar surface, and we can actually see a number of prominent rays departing from the Tycho impact. And so one of these rays travel more than 2,000 kilometers across the lunar surface and hit the back of the South Massif, and this mobilized some of the material of the South Massif, causing the landslide. But there is a twist to the story, and we now know that the light mantle is actually made of two distinct units, with different ages. And we know this because because lunar samples were collected from the landslide deposit. And so the young light mantle unit is something between 70 and 110 million years old, and the old light mantle unit is twice the age. And so if we have two landslides far apart in time, then we also need two triggering events. And so the Tycho impact is not enough. It will just be able to explain one of the deposit. So we need to find a second trigger event. And we may, well, I found, or we think that this linear feature that run across, I hope you can see my point, that this linear feature that run across the landslide deposit in the valley, the dark valley here. This feature is called a lunar lobate scarp, and it's a superficial expression of a fault. And so a fault is a surface where two blocks move one relative to each other. And so in this case, the terrain to the left, so towards the south massif, to the left of this fault, is pushed above the material, the terrain to the right of the fault. And so the idea is that the activity of this lunar fault, the shaking following the activity of the lunar fault, was responsible for causing one of the landslide, if not actually both of them. Right. So as I said, we have sample collected from the lunar deposit, and we can see here. So in orange, I trace the route that the two Apollo 17 astronauts made during the 3 days activity on the moon in 1972. And we can see they made 3 stops, called Station 2, 3, 4, over the landslide deposit. And so the view we have here, this oblique view, is a recent satellite image taken by the ongoing NASA mission, the Lunar Reconnaissance Orbiter mission. But we also have so many photographs available from the lunar surface that were taken by the astronauts in 1972 during their activity on the lunar surface. And these photos are now digitized and freely available online. And so here I kind of play around with some of them to create this mosaic. And these photos were taken at the landing site next to the lunar module, and it's a panoramic view of the mountain, the one that we call South Massif, from where the landslide, the source area of the landslide, is probably placed here at the summit of the South Massif. In these photos, the landslide is not really visible, and it's actually it doesn't really stand out topographically. Okay, probably some sort of shaking, or with time the edges were kind of smoothed out. But with a bit of careful observation, we might be able, if we trust the description of the images, these thin layer that we can see here of this a bit darker gray compared to this gray of the terrain is actually the scarp, so the fault that cut through the landslide. These are a mosaic that I made, again, using original photos taken by the astronaut from the lunar surface, is from Station 2. And so if you remember one of the previous slides, Station 2 was at the base of the South Massif. And so the astronaut that took the photos is actually standing right at the base of the South Massif, which is here to the left of this image where these big boulders are. And look at the astronaut footprints just next to the boulder. So it also gives us an idea of the size of this boulder. And instead, in kind of in the midground of this mosaic, here where my pointer is. So towards the right of the slide, we see the lunar rover. So again, it gives a sense of scale of the landscape. And the lunar rover is actually standing on the landslide deposit that extend somehow in the mid area of this mosaic. So then the astronaut moved to station 3, and station 3 is where one of the many samples were collected from the lunar deposit. And actually this sample was collected from below the surface. And this drive tube is called, this instrument that we have here to the top right, this long stick tube, was used to extract like a core of the lunar deposit down to about 80 centimeters below the surface. And so the lunar rover had a TV camera on, and so many of the operation of the astronauts were recorded, and one of these was actually the collection of this core sample at station 3 of the lunar deposit. So here you read EVA2, that stands for extra-vehicular activity 2, and 2 stands for the second day of activity on the lunar surface. And this is a video. This is the original NASA video, which I cut. So it's now a 1 minute video. I just added a few texts just to make clear what's going on. We have original audio. So now I'm going to play it and for 1 minute, and we can just enjoy.
Copy that, check. Okay, I think I got it. I think I got it, Bob. Okay. Gene Cernan extracting the drive tube. Okay, Bob, 524 is what I think is a blue-gray rock. Probably the breccia. It's got a little dust covered. Copy that. From just off the rim of this little crater. If you see it, Bob, it's full. See that? Roger, we see a long thing in your hand there, Gene.
Okay, sorry, I managed to unmute myself, a bit of a spoiler. And there we go. So at the end of the video, we had a glimpse of the sample that was collected from below the surface, or a sample of the lunar landslide. And so the sample, the tube was then closed and sealed, and so to prevent contamination during the transport of the sample back to Earth. And so NASA has decided to keep some of the Apollo sample closed, waiting for future technology improvement in future technology to then study to a great level of details some of these samples collected in the 70s and 60s. And one of the samples that were kept closed is actually the sample collected at Station 3 that we just seen Gene Cernan extracting from the lunar surface. And yes, so in the sample was then opened in November 2019. And in this slide, we can we can really appreciate the improvement, for instance, in the scanning technology. And so the idea of NASA of keeping some of the sample closed for so long time, waiting for better technology, is actually paying off the waiting. And so at the bottom, so the bottom scan here of the tube was taken in 1974. We can see some clast appearing in the scanning, but look at the top. The top is the scanning of the same tube taken in 2019 with the X-ray computer tomography technology, and we can see many more details. We can see, like, in greater details, the clast, and so we can do, in a way, much better science now that we are waiting for almost 50 years with this new technology available. And here I'm going to show you a video of the scanning of the core sample. Okay, so we can really appreciate the level of details of the scanning. So here is a vertical tube, and then you can see the orange line moving down and showing the level, each of the scanning that form this, the all scanning of the core. We can really see great details of the grains, and hopefully some structures related to the landslide deposit. Remember, these are just only the first maybe 60 centimeters below the ground, below the surface, but still, hopefully they will provide important information about the emplacement mechanism of the landslide on the moon. And so now this the opening of the sample and the study of the Apollo sample kept closed for about 50 years is part of the ANXA, NASA ANXA program, and ANXA stands for the Apollo Next Generation Sample Analysis. And here we have two images. These are from the NASA Johnson Space Center in Houston. In the photo to the left, we can see the tube still closed and sealed. To the right, instead, we see the sample roughly here below the left-hand glove, opened for then analysis. You can see how carefully it's been kept, so to prevent any type of contamination, especially now that it's being open. And so this is something I find extremely remarkable, the long-lasting legacy of the Apollo program. So from the 60s and 70s, how we can still do a lot of science using the Apollo data, the Apollo, the sample collected by the Apollo mission to the moon, and the ANXA, the ANXA program, the NASA ANXA program, is some sort of bridge, or at least what it's aiming for, bridging the Apollo program for the lunar exploration with the current NASA Artemis program for future lunar exploration. So to then send human, the first woman and the next man, back to the moon by, I guess, the end of this decade now. And so hopefully very soon we will be able to have more sample back to Earth from the moon, and be able to continue to do great science with lunar samples. And this is my last, this was my last slide. And so thank you so much for following this presentation, and I hope you enjoyed. And I will be happy to take any questions you may have. Thank you.
Hi, Julia. Don't seem to be able to start my video yet. Can you hear me okay?
Yes.
Okay, that's brilliant.
I...
Well done. There I am. That was a really awesome talk. Thank you so much. It was so interesting. And I love all the imagery and everything that you've got in there. I just want to, because it's so exciting that you've got this sample that's been opened after all this time. And so I was just wondering if you could just tell us a bit about how you're going to use that sample, what it can tell you about these landslides.
Yes, so I still have my share screen, but I just moved back here without let's show it again. It's just so cool. So yes, as Lucinda mentioned at the beginning, I'm involved in the ANSA program, and I will actually look at these scanning images of the sample, and so to try to make a 3D analysis of the structure of this core sample, looking at grains, if they have any type of features, the way they are maybe oriented, or any other like hint about possible mechanism of emplacement of the landslide. So yes, so I'm really looking forward to look at this data and trying to get some extra information about the landslide. Yeah.
Brilliant. That'd be really exciting. Look forward to the papers coming out on that. Okay, so we've got a question from Steve Evans. He said, how do you know that a surface on the moon is the result of a landslide rather than a volcanic flow?
So, volcanic flow, for volcanic flow, you can actually have landslide that originated from, let's say, a collapse of a volcano flank. And so in that case, you still have like a debris, like a rock forming the volcano, or in this case, a mountain. In case of volcanic flow that are then linked to maybe magma activity, you would expect to see some glass, also grains, so that derive from almost instant cooling of molten lava. But in the case of this landslide, they which I then maybe show another image here. So because they sample the landslide and they were in place and looking at the boulders and the material forming the landslide deposit, and looking at the boulders that form the South Massif, they were able to say that in this case, the landslide material, the material forming the landslide, derived from the South Massif, because they are made basically of the same type of rock.
Okay, that's great. Thank you. So someone's asked quite a general question, but actually it feeds into quite a few of the questions that we have had. When you're looking at sort of comparing all the different sort of planets, the landslides on the different planetary bodies, can you tell us a bit about what the factors are that affect the landslides, or the impacts of them, how destructive they are? Does it make a difference which planet it occurs on? Does less gravity make a difference, or are the factors more to do with material incline, size and shape of the soil and the grains? So I don't know, that's quite a big question.
Yeah.
It does incorporate quite a lot of the questions that we have.
Which is actually like represent the big question that we still have about long-runout landslide, because in this presentation I showed landslide on Mars, Earth, and the Moon, but we see this long-runout landslide on other planetary bodies in the solar system. I think on Venus, they identified a potential long-runout landslide, possibly on Mercury fairly recently. But in let's say beginning of 2000, and then with the recent mission, Cassini mission, or the mission to the Ceres, the dwarf planet, long-runout lens have been identified. And so also in Iapetus, one of the moon of Saturn, or the New Horizon mission to Pluto, imaged some long-runout landslide on Charon, which is the moon of Pluto. So it's obvious how these long-runout landslides are a very common landform in the solar system. And so it's absolutely like, the main question is like, okay, how comes they are so common? And how gravity may be affected, because we know gravity, depending on the planet or moon, is changing. But it looks like that, despite the fact they are on different planetary body, and if we consider also on Earth, we have ice, we have water, and other places we don't have an atmosphere. Regardless all these differences, we still have the same type of landforms. So I don't really have an answer, just like even my putting out there information that makes like, oh, wow, these are kind of remarkable landslides for which we don't really have a clear answer. So one of the things is like, do we have just one universal mechanism that would be able to explain all these landforms on so many different bodies? Or instead we have different mechanisms that then would be able to produce the same type of landforms. So this still remain an open discussion.
Okay, yeah, that's interesting. So John Miles asked a question. How do the soil landslides compare to snow avalanches that sometimes travel further than expected? So again,
yes. So, well, this is so also snow avalanches can be actually really fast. They can gain velocity while entraining more snow in that and increasing their velocity. I have to say, I'm not sure how the two would compare. And one thing I have to say, which I think maybe kind of trigger this type of question, is that this landslide, let's call it the light mantle avalanche landslide, looks completely different, I would say, from the other type of landslide we have seen on Mars and Earth. And I understand that maybe it resembles something made of much finer material that might resemble something like the snow avalanche, but I'm not really sure I would be able to reply, have a ready answer for that, because then still it remains let's say a puzzle, understanding actually how the light mantle was in place. It still remain unexplained, the mechanism behind that. Yeah.
So do you have an idea, like some people are asking here, about the actual sort of velocities, about how fast these things would travel?
Yes, so this is something I probably slightly touch on when I mentioned the 1881 terrestrial landslide, the first one that was described, and I said it moved about what did I say? Several tens of meters. I think it was estimated 45 meters per second, which is kind of fast. And the other lens, obviously, and in a way, luckily, we don't really witness long-runout landslide that frequently on Earth, or at least this big. I moved to another slide, so that will help me to then reply. So the way the velocity is estimated for this type of landslide is based on indirect observation. And so in the case of landslide that are let's say running over an obstacle, so is a approximation, but you imply like an equation where you had the transformation of potential energy into kinetic energy. So working out from that equation, you can get an approximation of the landslide. And now I'm going to the answer. So it's found that they can move up to 100 meters per second. So in terms of kilometers per hour, they can range from maybe 70, 80, and some of the modeling may also say they can reach even 200 and more kilometers per hour. So moving like a Eurostar train. Remember, these derive from indirect methods based on some approximation, but it gives an idea that all these landslides were actually fast. Yeah.
So the other thing that people are really interested in are the landslides on Mars and the ages that you were saying. So you've got these really ancient landslides on Mars. So I think some people want to know if you know how old they are. So Christoph Kreuter, how old is the first landslide shown from Mars? Do we know? And then somebody else who's fascinated by this has asked about erosion. So I mean, I don't know how long do these things last for?
Yes. So going back to the age, so the way that any surface on extraterrestrial planetary bodies is determined using craters. So is a statistical method. So by counting the craters and also of a certain size, there are some equations that are able to telling us the age. So I put it very simple, okay? So some papers have done this for landslide in Valles Marineris, which is this long canyon on Mars. And so from that study, it turned out that the landslide covered span from 3.5 billion years ago up to maybe 100 million years ago, or even slightly younger. So in a way, they cover, if this type of method is correct, it's telling us that this landslide has always occurred on Mars throughout the history of Mars. And so, as I said, some of these are hundreds of millions years old, and some others even older. And so the question about erosion is it's a good one, because you think on our planet, landforms are easily eroded away by, I don't know, rains or any other atmospheric weathering and all sorts of stuff. But on the surface of Mars, these landforms look just so pristine, like they happened, I don't know, yesterday or a few weeks ago. And so this is actually very interesting, because either the dating is, let's say, not precise, and they are much younger, or this is actually telling us something about the processes of Mars. And so that maybe we have some active processes, but they are not so efficient in eroding and obliterating, let's say, the morphological record of this landslide. Yeah.
Brilliant. Thanks, Julia. I'm just going to ask one more question because we're running out of time.
Sure.
So we've got a question from Jane McClelland. What samples would you like brought back from the next lunar mission? Which landslide? And do you know where the next mission is aiming to go?
So if I'm not wrong, the next mission will aim to be around the south pole of the moon. And this is because it's an area where you have area almost always illuminated by the sun. And so this will help the human mission there. So that would be roughly the area. I'm not aware there will be a landslide there ready, maybe. And hopefully there won't be any new while we explore the south pole region of the moon. But I don't know. I think I'm showing this image here, and this is a very big one. Ideally, I know this is impossible, but I'm gonna say I would love to have a big core, not like those 80 centimeters. But obviously for technical reason, it won't be able. So this landslide is like hundreds of meters thick. It would be nice to have an entire section, like they do with the ocean drilling exploration on Earth. And it would be really nice to then be able to reconstruct the entire, in this case, stratigraphic column of a landslide deposit. That would be awesome, but I guess very challenging. Yeah.
Absolutely. Well, that's something to aim for in the future. That would be really great. I'm so sorry I can't take any more questions now, but I'm going to hand back to Lucinda. So thanks again, Julia. Thank you.
Thank you.
Oh, no, please stay on, everyone. I just wanted to have us all on here to say goodbye. Thank you so much, Julia. It was amazing. So interesting and incredible. And of course, I'm a huge Martian fan, so I know our little cache samples are really tiny to what, but a lot more science to do. So exciting. It's been wonderful. So that's the end of the 2020-21 Public Talk season. A big thank you to all our speakers for being with us through 2020 and to here. It has been an epic journey, and we are all grateful for your generosity in being with us and all that you have shared. You can join us again in October when we kick off the new season, and we already have some exciting guests lined up for you. We hope you will join us. From all of us at the Royal Astronomical Society, bye for now. See you in October. Thank you.